This is, with the next slide, I think, a good way of characterizing the idea of making sense out of chaos with global modeling. And what we have here, you can ignore the bit at the bottom. I just couldn't quite make it all get to that one picture. But the main picture there is showing different levels of greenhouse gases going out to 2100 and the associated change in average global temperature in Celsius with those different scenarios. And if you start at around 40 gigatons of CO2 in the year 2000, we've got to make that go down to basically close to zero or below zero, depending on the uncertainty there, to keep climate change at something on the order of 2 to 3 degrees. And if we continue on the path we're on and keep ramping up, we're possibly as high as 8 degrees of temperature increase, which is a pretty devastatingly bad planet scenario. Even 6 is pretty bad. But you can also see from that chart the huge bounds of uncertainty around those things. And naturally, I mean, we're looking out, 85 years, and we're, I think the science is improving. Some of the near-term stuff is clearer than it used to be. And I think with each assessment report, we're finding that we have more of the puzzle pieces in place. But still, there's a lot of chaos on that chart, and the relationship between these different things isn't clear. Obviously, the one takeaway we've got is that if we can cut our greenhouse gas emissions, we're going to have lower temperatures. So at the IEA, they tend to take these figures, and then they, at the International Energy Agency, where I worked for 10 years, they start with those kinds of IPCC things and then build off of them and try to understand, well, what does that mean about how we should change energy use in particular. This figure includes all greenhouse gases, so it's got agricultural greenhouse gases and other things. But here's a figure, it's actually based on the 4th assessment report that came out last year that the IEA did. And here's how we take chaos and turn it into pristine science. We just draw the average line, and you don't see any of that messy uncertainty anymore. You just have one simple line that shows 6 degrees, 4 degrees, and 2 degrees, and we start from there. So that's really the crux of my talk, that you just get rid of all that uncertainty, get rid of the error bands, and just put the average and then call it a day. But it's the same story, of course, and we don't even, I think the 8 degree is kind of something that's coming along that we weren't even thinking about 2 years ago. But the big news is, I think, that we have a decent shot at a 4 degree scenario if we can cap global energy-related CO2 emissions and then deal with other parts of the whole global system. We can cap it at 4 degrees. It's still a very damaging scenario, and if you look at the Working Group 1 kind of reports and Working Group 2 kind of reports, you see that there's still a huge amount of disruption over the next century and beyond, even in a 4 degree world. And the best we're going to do is, keep it at something like 2 degrees, and that's getting increasingly hard. And you may have seen any number of studies and press releases in the last, let's say, year or two that question whether we can still achieve this bottom line here. And you can see that it means that by 2020, we have to be on a downward trajectory. And we're still on an upward trajectory. Even in, let's say, 2013, it was higher. It was about, I think, a half a gigaton higher than 2012. So we're not there, and to turn that corner is a pretty big challenge. So quite a bit of what I talk about relates to that idea. Here is how we've translated that, again, into some very simple, clean-looking averages, or at least, let's say, one possible future. There's any number of possible futures that could have a result like these results. But this is the way the IEA, using one kind of model, this is from the Energy Technology Perspectives model, which is an optimization model, trying to find the low-cost way of achieving a low-carbon future. You've got the 6 degree, the 4 degree, and the 2 degree, linking back to the last chart. And you can see here how much carbon is associated with different sectors and how much CO2 reduction we would need from those different sectors in order to achieve the 2 degree. And basically, by 2050, you have almost completely decarbonized the power sector, and you do completely decarbonize the power sector shortly thereafter. There's another version of this that goes out a little farther. Industry and transport still have some carbon. They're not quite there yet. And then residential is also almost completely decarbonized. So it's a challenging picture. You're talking about every building in the world becoming basically zero net energy buildings, or they're running on electricity that is decarbonized. And even for transport, if you compare the light blue to current, or 2009, or say the 4 degree, it's about half. The emissions in transport are cut by about half. So it's still pretty challenging, and one reason it's challenging, and I didn't quite get these in the right order because I should have put this one. One reason transportation is challenging is because of the growth, and this is just an example of the kind of growth that we are seeing. We are not expecting to see a lot more increase in travel, in car travel and car stocks in the developed world. So this is, IEA tends to break things into what we call OECD countries. Non-OECD countries is pretty much like the developed world and the developing world. And I guess so the good news is that, at least as far as cars and light-duty vehicles go, the stocks we're getting towards saturation. But in the developing world, it's still growing, and it's going to grow a lot in the future. And so, it raises this question of how are we going to decarbonize that sector at the same time that the sector is growing extremely rapidly. And, of course, this is true for a lot of things. So I'll back up now, and we'll get back to that point. Here is the IEA picture from the World Energy Outlook, which is consistent with the energy technology perspectives, on one way to do it in terms of not sectors, but in terms of different kinds of activities. The WEO, typical IEA, that uses the concentration of CO2 in the atmosphere. It's the 450 scenario. That means 450 ppm, which is pretty consistent with a 2 degree kind of scenario. And I think it's very revealing, and I think we see this across a number of different modeling exercises, that efficiency, there's still a huge amount of untapped efficiency out there across sectors. So for transportation, for buildings, for industry, and for electric power, we can get about half of the needed CO2 reductions from energy efficiency improvements across these sectors. A lot of it is so cost effective that it raises all those questions about why doesn't it just happen, and that leads to the whole field of behavior, both industry behavior and personal behavior, and discount rates, and all the different reasons why the low cost opportunities are not always taken. But so probably we're going to need a lot of policies even to get those efficiency improvements, even though in some cases they pay back. Even if, let's say, 3 years that you make an efficiency investment and you get the return. But there's also a wedge here for renewables and nuclear and CCS, and there's biofuels. There's also a lot of bioenergy in the renewable part. But one of the things that then comes from this is the question, well, what if you didn't have expansion of nuclear? And very worryingly, really, when you do this kind of modeling, what if we don't get much CCS? Because we're not getting much carbon capture and storage happening yet. Nothing like what was hoped, let's say as recently as 2010, what was hoped would be in place by 2020 is just not happening. They're not really getting past a few demonstration projects. So if you take those wedges out, it makes the whole job that much harder. So that's kind of an overview of some of the IEA modeling that's been going on. I put this up because I think these are really interesting questions, and maybe at 20 after we can start to talk about some of these. I'll try to touch on them. I don't promise to touch on all of them, but I think the kinds of questions we'd like to be getting at with our crystal ball are, what will the world be like in 2050? We're going to have 10 billion people instead of the current 7 billion people. They're going to be wealthier. That's partly mostly a very good thing. I hope that people are wealthier, and B, that it isn't all happening with the 1% globally, that we get some distribution of wealth increase. And I think we're beginning to see some concerns about that. China, it's becoming clear that China's Gini coefficient, the distribution of wealth, is getting worse fairly rapidly. They're getting their own kind of 1% going on over there. So that distribution of wealth probably has a big impact on a lot of this. And I don't think anybody's doing a very good job of understanding how wealth increase along with distribution of wealth in the future might affect a lot of these dynamics. What are the low-cost pathways? And we technologists, I'm certainly not an engineer, but I'm very interested in technology, and it's very convenient to assume that if we build it, it will get cheaper. And so I can talk a little bit about that. But we really are hopeful that a lot of the technologies that are coming in now, one of my favorite topics is electric vehicles, but I think photovoltaics is another one that's actually come quite a bit down the cost curve. And can we keep getting that kind of success, and how much are we depending on that kind of success from new technologies for our results? And I have to confess that we really are. That, for example, one of Lee's areas, cellulosic biofuels, play a big role in these scenarios, and we basically assume that they will eventually get pretty cost effective if we build enough of it. So that's an issue. I think the resource questions are very interesting. We have certainly declining resources, and yet sort of year by year we keep finding more. And I think the fracking revolution in the U.S. is a very interesting example of a situation where we kind of were expecting declining resources, and suddenly we have more gas and almost more oil at the moment than we know what to do with. Lifestyle. Behavioral change, it's huge. It's easy to just assume we can't have any, and so you just try to keep the lifestyle part of this modeling the same through into the future, and don't challenge anybody to change the, let's say the way that they travel or the way that they eat. We just try to accommodate current lifestyles, and that's not realistic, but it's very hard to figure out how would you assume it can change. And I guess I covered the technology thing, but infrastructure. I think another area that doesn't get covered very well in a lot of modeling efforts is what is the role of infrastructure. Some kinds of infrastructure that we've already got could lock us into certain pathways. There could be infrastructure-related constraints on systems that we're not capturing very well. So those are all things that I don't feel like I have that many answers to, but I think are very interesting questions. So exploratory scenarios can do different things. I think, maybe the hardest is to do policy scenarios where you try to understand if you want to get to a certain place, what has to happen to get there. And for example, the slide I showed with the reductions with the wedges, that's nice to see that we can get certain reductions from different things, but actually making it happen is pretty much a policy set of questions. And understanding, A, what a particular policy or combinations of policies are capable of doing, and B, are those policies even feasible? Can we get the political will to do them? Are both challenging, and to do both at the same time it gets depressing, because let's say in the United States, we're not even going to talk about new taxes for most things, right? Increasing taxes on bads would be a big step. Putting a CO2 tax in place would be a big step, but it's really not on the table. So you got to figure out other things, and then we often come up with some fairly tortured policy ideas, to the second best and third best approaches to get around those things. If-then scenarios are very nice. We can do a range of different futures and understand that if this changes, then that changes. I kind of like those, and the kind of modeling I do features a lot of if-then, because you can rely on a lot of sort of real relationships, accounting relationships between things, actual equations that are identity equations. If you have so many cars that drive so far and have a certain amount of efficiency, you will get a certain amount of fuel use. And so you know that if you have more cars and the other two things stay the same, you're going to get X amount more fuel use. Those are nice, you can play, but they're not very realistic because you're not getting in the dynamics that we see around us, all sorts of things. And then the same idea, you can do sensitivity analysis and uncertainty scenarios, and increasingly I think we're seeing people handle uncertainty by doing things like Monte Carlo, running large numbers of scenarios with probability distributions and trying to tease out what are the most likely combinations of things that could happen to add some robustness to the future scenarios. And that's pretty much all I'll say about that. I don't have time to get into that stuff, but we can talk about it. But I'll just give you some examples now of different kinds of modeling and what we're finding. And I think this one, I hesitate to put this into my talk because I think it's pretty damaging to my credibility for this to be in here. But and it's fairly new. And actually, the guys I'm working with probably don't know I've put it into a slide, but I think it's fine. I think other people are starting to use it. So we've got a group of four modelers, four teams that do modeling. One is called GCAM. It's a global change assessment model. It's got a lot of land use, and it's also got energy. And then there's the IEA mobility model, MOMO, which is the transport model that's part of their ETP modeling system. There's a NGO called ICCT, which has a transport model called Roadmap. And the last one is from IASA, the Institute of Applied Systems Analysis in Vienna, and they have a message model. The message model is an optimization model. GCAM is an equilibrium dynamic equilibrium model. MOMO is part of an optimization model, and the ICCT roadmap is more of a, econometric model. So with econometric type projection. So they're different models. But what's amazing, as hopefully you've been staring at this, is that with these four example countries from a recent set of baseline projections from these four models, you see some wildly different projections, especially China and India. So this is the number of two-wheeler, basically motorcycles, and four-wheeler vehicles on the roads in these countries in 2005 and in 2050. And luckily, the 2005 numbers are pretty similar, because that's data, but they're not exact. So we're starting to look at why even the 2005 numbers sometimes aren't identical. But we don't understand yet why, for example, two of these models is projecting almost 1 billion vehicles in China of four- and two-wheelers, around 600 million cars. And the other ones are down around, one is at 200, one's at 400. Some of it has to do with differences in the projection of incomes. Some of it has to do with basically the relationship. I think a lot of it has to do with what you assume about the relationship of rising income and car ownership. But some, at least I know that in the message model, you have feedback loops that limit the growth in cars as a function of certain kinds of limiting factors like road availability, and also there's a higher shift to traveling by other modes. I guess in urban areas, cars don't grow as much as they do in the baseline of these two middle ones. So we'll explore that and we'll try to understand that better, but that's a kind of chaos, right? That's a kind of a thing that I think it's very useful to compare different models and see what they're saying. What I will mention is that here's one thing that we did with MOMO, which I think is a very interesting first, very baby step toward thinking about infrastructure. So if we project a certain number of cars out there on the roads, and these are global models, they're not down at the level of resolution of telling you what's happening in a given city, but if you add up all the cars and the amount of driving that is likely to be happening with all those cars and trucks as well, and then you look at the road networks in these countries. So we spent a lot of effort over 2 years at the IEA to get the data compiled on the road extent in countries around the world and breaking it down to the lane kilometers of roadway. And this just simply takes the ratio of the vehicle kilometers of travel to the lane kilometers of travel. And of course, if you're thinking about traffic congestion, it's really, a lot of it's about time of day and rush hour and that kind of thing. So the overall annual average is not a very good indicator, but it tells you something. And it was very interesting to see how different countries line up. The orange circles are 2010, and the bigger the circle, the more cars we're talking about. And if you look at the summary picture for OECD, and then you go out to 2050, which is green, I think you learn something. At least you learn something about your own projection. OECD, because there's not that much growth in the car stocks, and there is expected to be some continual growth in road capacity, it really doesn't change very much. So on average across the whole region, we don't expect to see a big problem with the ratio of the number of car miles to the lane miles. But in non-OECD, it's a different story, and it's because there's so much car growth expected, and even with actually making some pretty heroic assumptions about adding roadway capacity, you get this kind of a picture. So you see the circle getting bigger, the more cars. But the one that scared me the most and continues to is India. India actually starts pretty low because there's a huge rural road network in India. I don't know whether those roads are going to matter that much, actually. But if you even having that network in place, the increase in the ratio of car kilometers to road kilometers is so dramatic in this kind of scenario in India that they become one of the highest ratios in the world by 2050, and I really question whether they can provide roads at the rate that they would need even to do this. So this is an area that we're looking at more now. In fact, we're looking at 4 cities and 4 geographic areas of India to try to do a bit more of a micro-analysis and see if we can understand, what this looks like when you take a little bit of a deeper dive. But it does make me question whether our projection of car ownership for India and China and places like that might be not possible in 2050, or in some way create so many problems that that there are feedback loops that would keep it from happening. Okay, let's see. Here's another topic that I think is kind of interesting, and this is about technology. This is getting into alternative fuel vehicles. We are projecting the need for basically a complete transition from gasoline and diesel fossil fuel vehicles to zero carbon vehicles. The new ones pretty much have to achieve this transition by 2050, or we have to be a long way toward a world with electric cars and or hydrogen cars and or cars running on biofuel if the biofuel is really low greenhouse gas biofuel. And one of the things I mentioned was the heroic assumptions about technology. And this is a lovely chart if you believe it. This chart comes from the National Research Council, which is a very esteemed body that pulls together experts to produce research. And they published last year a new report on alternative fuels and vehicles, light-duty vehicles for transport. And they did a new assessment of the cost of different technologies, and I see that actually this doesn't show what all these acronyms stand for, but the most expensive was estimated to be battery electric vehicles in 2010, that these were on the order of $16,000 more for an equivalent vehicle than gasoline vehicles. Other ones are closer, but you've got hybrid electric vehicles, that's HEV, and you have plug-in hybrids, PHEV, and the bottom black line is the base gasoline vehicle. That does get somewhat more expensive over time, partly because of things like more pollution control and better safety equipment that actually happens to other vehicles as well. But amazingly, all these costs come down over time until by 2040, you have this convergence. So all cars end up costing the same. And I think this is first cost. I think it's the upfront cost of the car, so you actually are doing even better if you're saving fuel, which some of these technologies are going to save you in fuel cost. The one exception is plug-in hybrid vehicles. They never get quite as cost-effective, but they're pretty close. If this happens, then it's going to be very, very helpful to this transition, that we can move from gasoline vehicles to these other vehicles as they get cheaper. They'll also get better in other ways. And it makes the policy picture for this a lot more possible, because we're probably going to have to subsidize a lot of these vehicles until those costs come down. The problem is that the reason all these costs come down is that there's two reasons. One is that they can imagine how the costs come down. There's the technology analysis and the engineering cost analysis that shows you, here are the reasons why these costs come down. A lot of it has to do with, there's scale, there's various kinds of R&D related improvements that are expected, but then there's this whole optimization part, the technology learning part. And technology learning is typically analyzed as something that happens as you get better at building. It's a function of how many units you've built, and so with every doubling of production you get some kind of a cost reduction. And there are plenty of nice charts that show this for a range of technologies. So we tend to assume it can happen for other technologies. And I think batteries are really the key thing here, that battery costs come down very dramatically over time. But in order to make that happen, we have to sell millions of these vehicles. And so, of course, the risk is that we go out on this limb and we support the buildup of these new markets and these new technologies into these markets with the policies to make it happen, and if the costs don't come down, or even if they don't come down fast enough, you get into a real risky situation where the policy could collapse. And I think even already we're seeing problems with that. California, well, the U.S. has a $5,000 subsidy on electric vehicles. Some states have another $2,500 subsidy, and I don't know how long that's going to go. I think that could get pulled at any time. And, the political system is such that these things are almost annual decisions about whether they're going to continue to fund programs like that. But we probably need at least that level of subsidy, out to 2030, even in this very happy picture. So I think, that's the kind of thing that modelers can't really answer those questions. But you got to be a little careful that you don't over-rely on assuming that that's all going to work out. Meanwhile, here is a picture of market penetration of these new technology vehicles that I did in a project for Norway last year. And Norway is very interesting because they actually have the highest share of electric vehicles right now in the world. They're the world leaders on electric vehicles, which isn't saying much because I think their sales share actually reached 10% for a few months last year. I think the average last year was 5%, which is pretty impressive. And not only that, the number one selling car of any kind in Norway in September was the Tesla S. The Tesla actually was the number one selling car in Norway. So they're into it. They're not a very typical country, but what they asked me was, well, if we could do this transition and move away from gasoline and diesel cars, what do we get for it? And so we just, using this mobility model, we just walk through a scenario that if you had this picture of market penetration of new technologies, we can track what it does to the stock of cars, and we can track what it does to the energy use of different kinds, and then to the CO2. And I'm not going to show you all that, but I just thought I'd show you this, partly because it looks pretty amazing. And the first thing is, we initially said we told them, okay, so how about we try to have no conventional gasoline or diesel cars by 2050. So the gasoline is the dark blue and the diesel is the bright orange color. And after we'd done this for a while and looked at some of the results, they came back to me and said, nah, that's not challenging enough. Let's do 2040. So we went back and we did it in 2040. So they reach no more sales of gasoline or diesel cars by 2040. They've got plug-in hybrid electric vehicles. They've got that are almost down to very low share by 2050. And then it's all electric and fuel cell vehicles. So this is a picture. What is it that's going to make this happen? Well, they're actually working on policy strategies to try to make this happen. And I'll be going back there this June to talk to them about some of that stuff. And, it's amazing when you're in Norway and you are at a conference like at least the one I was at, there are actually delegates in the room from their legislature who are listening, and they're people who actually make policy. And it's just what happens when it's a small country. It's incredible. But what I'm trying to warn them about with this scenario is that this is incredibly rapid change. It may be possible for a small country like Norway to pull this off. They're not a car manufacturing country. It makes it a little easier to do policy that requires rapid change. But the rates of change here over, sort of a 20-year period are fairly unprecedented for the car industry. To change your drivetrains and your propulsion systems and your fuels that rapidly and build up the refueling infrastructure that rapidly. I think there's a lot of questions around that. And I'm not sure that we have models that are very good at assessing the rate of change problem and whether there are limits to how fast we can, pivot to do that. But it is certainly the kind of picture we're going to need, maybe another 10 years or so, or 20 years in this country, to be on a path to a low-carbon future. Okay, now I think it'll probably be the last topic I have time for. I'll talk a little about oil. I just think it's pretty interesting. So, part of the connection here is that we do tend to assume when we do these kind of studies, we do tend to assume at the same time oil prices are going to rise. And so that makes everything else look better. And there are two problems with that. One is that oil prices keep not rising. They rise for a while and then they go down. And it turns out it's very volatile. It's very cyclical. There are things about the nature of the oil markets that, as prices rise, it turns out, wow, it's called economics. You get a big incentive for more exploration, for developing new kinds of resources, and new technologies come along. And the big one now is tight oil, fracked oil. And in the United States, it really started as a natural gas thing that we figured out how to do the fracking and get the gas out. And after a couple of years of that, it began to be clear that there's also good chances to get oil that way, and also that maybe we have more gas than we even need right now. And so here is BP's projection from last summer. They now project an increase in oil production that is a 45% increase between 1990 and 2030. But what's important is that one of the biggest sources of increase in global oil production is tight oil, which is effectively fracked oil. And on the right, you see where it happens. It's almost all happening in North America. U.S. is becoming the biggest source of additional oil supply, and this is expected by BP publicly to go on for quite a while. It kind of starts to level out after maybe 2025, but right now we're in that huge rise period. But they also expect to see some from Russia, and you never know how this is going to change. It could be that they're overestimating some things, but there's a tendency to suddenly find out that there's a bunch more somewhere, and this thing keeps getting bigger. So we'll see. This thing could flame out. I'm not an oil specialist. I read about it, but my sense of it is that, even though a lot of people are skeptical about how long this is going to go on, it wouldn't surprise me if this picture keeps going for a while, which means there's definitely a dampening effect on oil prices. Oil prices are probably something like $10 or $15 lower right now in the 90s than they would be if this hadn't happened. If they get low enough, then that might cause this to stop, because then you lose your incentive to produce more expensive crudes. But one of the effects of this, there's two effects I'll show you that are interesting in the context of trying to cut carbon emissions. Here is the associated picture of North American oil imports. Okay, so this is from 2011 to 2035 in relation to the increase in U.S. oil production and other things. So it's broken out here. You see the demand side efficiency. So that has to do with making cars more efficient and trucks more efficient. The U.S. now has very strong policies in place to make cars more efficient, and I think it's coming for trucks. We're going to see increasingly tight standards for truck efficiency, like big trucks. Biofuels are there, and a little bit of natural gas in transportation. That's mostly in long-haul trucking. I think that could end up bigger than they show. And then the increased oil supply is very important out to 2030, and then it begins to diminish. But that picture cuts the U.S. imports from 9 down to 3 million barrels a day in a 20-year period. And, that's a revolution in its own way, and it's a very geopolitically important kind of development. This is the same kind of thing, but showing more countries. There's the U.S. with how much it spends on the imports, and it goes down a lot between 2011 and 2035, but it's about the only country where that happens. At the same time, the EU is going up a little, but look at and Japan's going down a little just because their demand is going down. They import everything. But look at China and India. Their imports for oil mainly, but also a little bit for gas, go up dramatically over this time frame. So if this plays out, and it could be that 2 years from now this looks different, and the charts all look different. It's all crystal ball stuff. But using energy equilibrium modeling, there's reason to believe that the geopolitics of oil may change a lot in the next 20 years. So we'll just have to monitor that and see what that does. What I think the biggest thing in terms of climate change is we can't count on resource costs to drive this. We can't expect that oil will keep getting more expensive forever. I don't think anybody ever expects coal to get more expensive. But if we were successful in cutting the demand for oil, that's just going to cause prices to go down a little bit more, right? And as prices go down, it may reduce the production side, but it'll also mean more demand somewhere else and more carbon somewhere else. And so that's a kind of global elasticity that you have to keep in mind, that in a way we make it harder for ourselves. Every barrel of oil that we cut, we make it a little bit cheaper, and it encourages somebody else to use oil. So that's something that we've got to do our best to try to cover. So I think I'll just go to a couple of concluding thoughts here. In fact, I'll just do this one. I could have all sorts of different conclusions, but here are three things that I think are pretty robust, that different models find and that show up as part of our low-carbon future. And the third one is almost just a scientific truth, but we should be deploying efficiency technologies as rapidly as possible. They tend to be the most cost-effective, and there's a huge potential still for efficiency improvement. And I've got other slides that show that I think we can be cutting the transport demand for oil in half, basically for free, if we did efficiency to the max possible for transportation. Second, we need to get deep decarbonization of electricity generation around the world. It also tends to be among the more cost-effective things you can do. Very sensitive to carbon taxes and carbon pricing, much more sensitive than transportation will ever be, and a great way to get fuel switching in the electricity sector. And it's also very consistent with a general strategy of electrifying, let's say, the transportation sector. We need to have that decarbonization on the electricity side. And then third, let's just remember that, let's say fuels like natural gas are important as a midterm fuel. They're kind of a bridging fuel, but they are a fossil fuel. They're not particularly low carbon, and they're also a methane producer, and there's a lot of questions about methane from natural gas. The three fuels that have the clear pathway to very low CO2 are electricity, hydrogen, and biofuels, bioenergy. And we have to figure out pathways that get us to those energy carriers in a big way over the next half century. So, thank you. Do I pick them or you? Okay?
One of your 3 points, kind of long-term strategies there was to increase energy efficiency. And certainly that's politically popular. Everyone will agree that that's kind of
that's true.
So it seems to make a lot of sense. I've been concerned, been influenced by some readings recently on the importance of the energy rebound effect. The notion being that as you increase efficiency, people save money that they would have spent on energy, spend it on something else,
right? And
whatever else they spend it on,
yep.
Leads to an energy demand anyway.
Yep.
So you're not going to really save much when all is said and done.
Right. And that's
Are there answers to that? Is that considered? Nevertheless, energy efficiency still?
Yeah, I think it's the same kind of problem that I was describing about every barrel of oil you save makes it a little cheaper, and a half a barrel pops up somewhere else, right?
Exactly.
I think we need to be more honest about those feedbacks. In transportation, the actual rebound effect associated with, let's say, making every mile cheaper, because of the low elasticity of driving, it's not a big problem. It could be right, economy-wide, and also when you factor in that you're helping hopefully make incomes grow, then they're going to spend that partly on energy and possibly on fossil energy. So from the modeling point of view, it's very important to deal with these rebounds and try to represent them somehow. And in real life, it's going to be increasingly important. So what we need are policies that basically keep the price signal strong, even as things get more efficient. And so we have to figure out a nice way to say this that doesn't ruin the popularity of efficiency. But effectively, what you're saying is you'd like to see the tax on carbon or the tax on energy rising in a way that keeps the per unit cost fairly constant. That helps to prevent those rebounds. And then you could recycle that money into the economy some other way. Yeah.
In the last slide, the third element, you seem to dismiss completely the role of nuclear power.
Well, I said low carbon electricity. I didn't say couldn't include nuclear. Let's see here. I don't know why that stopped showing, but let's put that back up. Anyway, I don't have anything against nuclear power. I think nuclear, has its own set of issues. We all are pretty aware of them. I think, like I did say early on in the talk, if you don't have nuclear, if we don't grow nuclear power as a baseload option, that just puts more stress on the whole system. And it'll be interesting to see the extent to which we can use smart grids and advanced technologies and electricity management to allow us to go to higher levels of intermittent, mostly renewable wind and solar power. But the general, conventional wisdom is that once you get up around 40-50% of your generation is wind. In fact, I think Ireland somebody told me this. Ireland has now capped their wind because they're worried about letting it get too high. So if you don't have those, you're going to need some kind of baseload power, and nuclear is an obvious choice for that.
The scenarios that you outlined, which depend on rigorous policy response, XYZ thing, policy response, moving to electric, more decarbonization of the energies, needing a strong policy response. What do you might anticipate as the emotional kick in the tail to get some political figure somewhere in the world to take a serious look at climate change and heat oil and some of the constraints that are narrowing whatever gate we have to squiggle into the next generation?
Yeah. Well, that is really the question, isn't it? I mean, so we have a lot of ideas about what to do, but getting it to happen is hard. And what we do have are lots of little examples that are good examples that we can hopefully build on. Ireland is at 50% wind, or they're getting close to that kind of number. Germany had a day last year where they had 100% solar for like 2 hours on one day, but they were 100% solar. It's incredible. And and in this country now we've got a big shift from coal to natural gas. It might be because of fracking. It might be temporary because it may be related to the low cost of gas, and that could change. But it's a good thing. If we could stop building coal, for the moment nobody's ordering coal plants. If we could make sure that continues, that's great. We've got the cars in this country are going to be, if nothing changes to the current policy, they're going to be twice as efficient in 2025 as they were in 2010. I'm very interested to see what they're going to look like. They're going to be very light. It's going to be a revolution in the kind of vehicles we drive. So there are pieces of the puzzle that are beginning to move in the right direction, but you're right, we need a lot of big, heavy hitting still, and I don't see the political will. There's one response is that a lot of cities and states in the United States are doing things because they're not waiting for the feds anymore. And that's great, but there are probably some things that we need to do at a national or even international level, and I think that the number one international thing is we still have to get a price on carbon around the world, and that's going to be huge. It's going to have all kinds, even if it's not a big price, it's going to have a huge effect on the way we think about the problem and the way people plan. They're going to know that they're in that carbon-priced world. And the next big chance for that is next year in Paris. The UNFCCC, you know, they do the COP every year, and the COP in Paris in 2015 is the next, you know, you remember Copenhagen in 2009, that was supposed to have the big agreement, didn't happen, fell apart, and that was tough because from a political point of view, you had Obama fairly new, you had a Democratic Congress, and it really seemed like this is it. Next year, I don't know what we're going to have in terms of our own governance structure, but we'll still have Obama. But, you know, the big thing is, can the U.S. and China agree on a package, and then I think Europe will come right along, and I think that will get the dominoes to start to fall. But you don't see it. It's not obvious that it's going to happen. So, you know.
Have you taken a look at the EU and emissions trading, the ETS system and stuff like that? How do they have, has anybody evaluated the impact of those things in the long-term trends?
There are quite a few different, so that's an emissions trading system. It's like a cap and trade. And there are a number of those kinds of things. There are little pieces of it around, and Europe has a pretty big one. But that one is in a little bit of trouble because they haven't tightened the cap very well. And now the carbon price is very low in Europe the last couple of years. And so there's a lot of consternation. I mean, a lot of people sort of calling that one a failure right now. So they're going to have to revamp it and come up with a new schedule of CO2 limits. But in some ways, it's been very successful. I mean, I think with something like cap and trade, it's so complicated that just getting a system up and running and having it in place and making it work right is a big achievement. So then you just have to have the political will. Even with cap and trade, you have to set your carbon target and your number of allowances and make it harder each year. And that is unpopular. So the other thing that happened in Europe that's interesting is that there's a leakage problem. And the leakage problem means that if you don't do the whole world and you only do one place, California suffers from this a lot as well, you may lose business. Because if I'm being told that I have to lower my carbon emissions by 10% and I produce, you know, a widget, so I'll take 10% of my widgets and produce them outside of the system, right? I'll move to some other country. And so there's some evidence that some of that's happened. It probably would some of it would have happened anyway. It's all about outsourcing, right? So those things make it hard. They make it hard to do things without going global.
So you mentioned carbon capture, but you didn't really give your thoughts on it. So how do you view that in terms of a piece of the solution?
Well, I'm not very well informed about it, to be honest. But my sense of it is that it is the problem really is that no one really wins. I mean, there would be a small capture and storage industry, but it's nothing like, let's say, the PV industry, which is just now a massive, burgeoning, rapidly growing industry that's got some, industrial strength, and they can help to make the policies that they need. I mean, that's how the world works. You need industries that can fight for certain things. And the only thing that will ever happen with CCS is that power plants and big industrial facilities are going to have to put one of these things on, and their efficiency will go down 20%, and it's going to be more expensive, and nobody wants it, even though it means a lot less CO2. So it really will have to just be regulated, and everybody's moving very slowly on that. There's about 5, my understanding is there's around 5 demonstration facilities that were supposed to go up to 10, and then we were supposed to see some scale up, and that just sort of is stuck. So I don't know anything about the politics around that, but it seems to be stuck. And so I think, for example, this year with the IEA scenarios, we're likely to see scenarios that don't include it, or to include a lot less.
As far as global policy, beginning now, today up to 2050 is involved, 2 things show up on the graphs. One, the assumption that by 2050 we have half electricity for half fuel for transport and half fuel cells. Well, beginning now, isn't it very important to begin noticing what the generation of electricity is going to do as far as fossil fuels is concerned? We've got to generate electricity without fossil fuels, or
Right.
that doesn't fit.
Right. I mean, with electric vehicles, they're efficient enough that even if you got it down to, let's say 25% of your generation was from fossil fuels, that's still going to be better than running your vehicles on oil. But you're right. It's all based on the idea that we're going to decarbonize the power grid. And so...
But that's global policy beginning now.
Well, yes. And there are... I can at least tell you that in all the modeling work that goes on, that's part of it, that everybody's got the electric power grid decarbonizing, very rapidly. Whether we're seeing those commitments is another question. The world's power grid is decarbonizing at a pretty good clip right now, on average. It's a couple of % a year, but that'll add up. I mean, that's if you could do 5% improvement a year on something like that, you'd be doing fantastically, and I don't think we're there, but... The big thing is to stop building coal plants, and there are still coal plants being built in too many places, including Europe. But China and India are still building a lot of coal. China's big thing is that their coal plants are now CCS ready, so that they can put CCS on them someday, but they're not doing it yet. But anyway, yeah, I mean, you're right. We have to do both things.
Thanks again, Luke.
Okay.